I'm so happy to see many of you like my previous video about data science. I would love to share more about data science and machine learning, but my new movie is coming out soon and I will be very busy. I will let my apprentice Patrick to do the sharing sessions.
Hi everyone, this is Patrick again. I plan to create a mini video series talking about what is data science. I call it Data Science Explained like I am 5 series. Not everyone is into data, mathematics or coding. These are like alien language, especially if you are not working in a technical role. My initial plan was discussing papers, but I guess most people will lose interest. In order to deliver greater impact, I would try using simple words to explain complex concepts. If you would like to know more, you can search the related keywords to understand the full picture. I aim to use simple words and metaphor to explain complex concept. Use daily example to visualize the potential use. Talk as less mathematics as possible. At the end of the series, I hope audience can kind of tell what, why and how data science and help us to deliver values. Okay, let's begin the first episode. What is data science? If a decision or phenomenon is logical and not random, we believe data science can predict the outcome. If we have enough data. It sounds a bit too good to be true, isn't it? However, if you stay with me and keep listening, things will get more reasonable. For example, I ate sushi for dinner yesterday. It sounds random, but was it really a random decision? Can we build a model to predict it? Subconsciously in my brain, I may actually consider the following factors or facts before deciding to eat sushi. Do I like sushi? Weather is hot, I want to eat some refreshing food. My stress level is high and sushi is my comfort food. There is a new sushi bar newly opened in my area. The sushi bar has a dinner promotion. I haven't had sushi for a long time. Now, if I ask you to predict, will I eat sushi for dinner in the 1st of May 2023? You can't, you can only make a wild guess. No different from flipping a coin. What happens if I provide you some data? I'm okay to sushi. Temperature is 0 degrees, very cold. I just come back from long vacation, stress-free. There is no new sushi bar in my area. The sushi bar upped the price. I just ate sushi yesterday with my family. With these information, we would logically predict I will not eat sushi for dinner, right? What make the difference? Why now we can predict with confidence? Because we already have our very primal model. A binary sushi dinner classifier and data input to predict the outcome. Now pause the video for 20 seconds and think. Does everything make sense so far? If yes, let's move on. Now we apply the same concept of sushi dinner classification. Enter HCP rep trigger email RTE classification. To predict whether the HCP will open the RTE. Same to our sushi dinner example. What would be the possible considering factors for HCP? To decide open the RTE or not? Possibly HCP relationship with our sales rep. Disease interest. Number of related patients. New information or content, not an old news. RTE sent at an appropriate time. RTE content related to previous conversation with our sales rep. Anyone remind him to open the RTE? There are many unexplored potential factors waiting for us to discover. Ideally, if we have identified and have all the factors, we can make reasonable prediction, but most of the time we don't have access to the direct information. We can substitute or associate with other factors, for example, for HCP relationship with our sales rep. Can we create a new profiling category? Or associate it with interaction count? It makes sense to think if we interact with an HCP a lot, our relationship will be better. For disease interest, can we check any Viva dynamic attribute record? Or can we refer to HCP's webinar attendance record? Or Viva key message count? Does it make sense to think we would use more this key message if HCP is interested? For number of patients. Should we estimate it with product sales? More patient, more consumption, therefore sales is more. For the new information or content, it is rather straightforward. For RTE sent time, we can refer to the past HCP RTE opening record. For RTE content related to previous conversation with our sales rep, we can refer to Viva timeline to check any cross-functional team collaboration. We want to deliver the right message to the right customer at the right time. Now we have a binary RTE open classifier to predict will HCP open the RTE. We can selectively send RTE to those HCPs who are predicted will open. In other words, we can use data science to send RTE to the right customer. Also, sending RTE can now be an automatic task instead of manually clicking one by one. I know you may think this model is too simple. Yes, I agree, it will take time to explore what data is important for prediction. But as an example to share in this mini-series, it should be good enough. We have been collecting many data. It is time for us to brainstorm and reflect. What data do we need? Why we need this data? How we can use the data? What value can it bring? Frontline colleagues are required to input many CRM data and HCP profiling data, etc. They may feel frustrated if we require them to record many data as detailed as possible but not visualize or show them how their recorded data can help their daily work. It's time to start using data instead of collecting data only. Okay, now go back to our binary classifier. Binary means the output has only two options, for example, open RTE or not open RTE. For binary classification task, we have a sigmoid function to push the output value of our RTE open classifier into a number between 1 to 0. We can consider it as the probability of open RTE. If the probability is larger or equal to 0.5, then the output will be open RTE. If probability is less than 0.5, then the output will be not open RTE. Not every decision is binary. Sometimes we want to know the best outcome out of several options. For example, we have 20 RTEs. But which one should we send? Should we send them all? We want to predict which one of the 20 RTE content is most interested by HCP at this moment. So we only send that RTE. We want to deliver the right message. This will be a multi-class classification. This time we would not use sigmoid function, we use softmax function. Softmax function will convert the input into a probability distribution. Take this picture as an example. We have total 5 possible output RTEs. After the softmax function, it will become the probability of opening each RTE. All the probability values will be added up into 1. The RTE with the highest probability will be our output. Of course, we would need to change our model and training data to make it multi-class classifier. We may touch on it in later episode. Now we just need to aware that we can use data in that way. So far it sounds like data modeling is very easy, right? Provide this into this, then we will have this. In reality, things will not be that easy. For example, there are many important considering factors which we have never discovered or explored. Our available data is not enough to build a robust model. Even we know this information is important, we have no way to collect or access the information. For example, I know HCP will open my RTE if she is happy. But I won't know if she is happy at that moment. Data is dirty and can't represent the true picture of data relationship between input and output. We will discuss more in later episode. How we decide the correct weighting of factor. From the sushi dinner example, we know both price and weather will affect my decision. What should be the correct weighting? They should not be equally important, right? In past, we use human brain to decide the weight value and the result is horrible. Now we use machine learning model to decide the weight values. We have seen this slide earlier. We provide input into model, then have output. But we still need the weight value for each parameter in order to make our model works. Just like we use flour and oven will get bread. But we still need some additional information, such as how to make the flour into dough, how long and what temperature to bake the dough to become bread. These information is the weight value for each parameter in our machine learning model. Take supervised machine learning as example. In real life there are many different structure and layer architecture. Complex model can have more than 1 terabyte of parameters. In here we simplify to the max to make it only 1 layer for illustration. This is an equation we saw in high school. Y is equal to mx plus c. In machine learning world it would be output is equal to model weight multiply with data input then plus bias term. Just the m, x and c are actually matrix values with many dimension. In here to make it even easier we assume bias term is 0. And we don't have activation or regulation layer. So output is equal to model weight multiply input. Y is equal to mx. At this moment, you seem understand something, but also very confused and have a lot of questions. It is normal because to fully understand the full picture you cannot rely on this mini-series. Here I can only give you a rough idea. By the way, this guy is Andrew Ng. I think more than 70% of data science people in the world after 2010 have watched his teaching video to know what is neural network and machine learning. You can also give a try if want to know more. Here are some take-home messages. There are so many different type of machine learning deep learning models. There is no fixed answer to say which model is better as it really depend on your data. Usually we would trial and error to test it out. The complexity of your model will determine how many parameters in your model to map the relationship between input data and output data. In other words, more complex model will have higher learning capability and deliver better prediction. But at the same time complex model will be easier to overfit. It is just remembering the data instead of finding the intrinsic value and pattern between data. It is common to see a simple model with enough data can beat a complicated model with not enough data. And also, the model is built by machine learning engineer or data scientist. How we build the machine learning model? It is by coding because computer can't understand English. We use programming language, mostly Python, to build the models. Some people will use R, but it is getting a bit outdated. Some industry or company will develop their own software to do the coding. To build deep learning neural network we usually use PyTorch. It is open sourced by Meta researchers. Or TensorFlow, open sourced by Google researchers. Years ago we had Keras, but it is now incorporated under TensorFlow. Data science or machine learning model can apply in every industry. But not every industry has in-house coding talent. Therefore tech giant like Amazon, Google and Microsoft are offering online platforms to provide ready-to-use machine learning models. You don't need to code, you just drag and drop some button like playing Lego. Then we feed our own data to the trained model, then we can get result. It is convenient, but the result accuracy and quality cannot be compared to tailor-made model. Just like a wedding dress we can rent in the bridal shop cannot be compared with a wedding dress tailor-made by Vera Wang. However, for imaging and language data, we will usually use their model as the base and train with our own data on top of it. Later I will share the reason. It is about transfer learning. Do you need to be great at mathematics to know data science? The answer is yes and not necessary, depending on your path. As long as you can understand the mathematics behind different type of machine learning model, optimizing, and regulation strategy, then it should be okay. Technically speaking, you can build the model without fully understand the mathematics behind. However, with a good understand of the mathematics, you can do optimization and fine-tune the model architecture better than others. This is also the secret sources I observed from many brilliant data scientists. If you are doing research, then you must be excellent in mathematics because you are going to invent a totally new model. And behind all the model is mathematics. Data science can be fun. When I was younger, I joined many competitions to learn and improve my skills. Before ending this episode, I would like to share one competition. Cornell Bird Call Identification. It was organized by Cackle and Cornell University in 2020 September. The objective was to create a classifier to predict the bird species by using 25 GB of bird vocalizations recording MP3 file with their label name. We usually see data in form of CSV file, image or text. How can we make use of MP3 data? That was the interesting part. Because sound wave and frequency are unique, we converted the bird MP3 file into spectrogram image. Then we treat it like a normal image classification task. There were total 264 different bird species, so it was a 264 class multi-label classifier. Sound pretty scary, right? I hope the RTE classifier has less classes. Did I win the competition? No, I was not smart enough. In fact, I have never won any money prize of those competitions. But I am happy enough to get into top 4% out of more than 1,000 teams and received the silver medal. Joining those competition is too stressful and tiring. I don't think I will ever do it again. Okay, I realize I have talked too much. My wife always scolds me about this as well. In this episode, we know output is equal to mx. How can machine train and learn the correct m value? Next episode I will share why and how machine can learn and train themselves to get the optimal weight value. Below are some keywords if you would like to research more by yourself. Stay tuned and wait for the next episode.